All right. Good morning, everyone. Really appreciate that you come here to my session though so early in the morning, and with the competition of 2 React sessions in parallel. So appreciate. I'm Robert Kubis. I'm a developer advocate for the Google Cloud Platform. What we are basically, we are your megaphone into the Google organization. So we like to understand our job as being bidirectional, in a way that we collect feedback from you how you use our products so that we can improve our products. So we like to hear how you use our product, like what ideas you have and things like that. If you have any like challenges with it where we can improve, please reach out. You find me on Twitter or on GitHub. Now today my topic is Google Cloud Spanner. To set expectations, I'm gonna talk a little bit about the history of Cloud Spanner and how we transitioned our internal Cloud Spanner into the cloud product. And then I go into like how Spanner works behind the scenes. And I do an attempt at some live coding. So fingers crossed that the demo gods are with me. So let's go back about 12 years. It's 2005 and Google is growing rapidly. And our AdWords business, which is basically our main and almost only revenue at that time, is on the back of a sharded MySQL. And we had occasionally to reshard that MySQL database, and the last reshard took actually multiple years. So that was definitely not a like feasible solution going forward for business that was growing that fast. So we needed something else. So what we needed is basically we needed a horizontal scalable system, but we still needed the strong consistency. I mean, this like business involved partners, it involved budgets, and involved money. So we had to have that like correct. We couldn't like sacrifice on the strong consistency. And what's really important here as well is the system was running 24/7. Our business was 24/7 around the globe, right? So any downtime of this was losing money big time. So we had to build a system which allowed us to evolve and innovate without any downtime. So we built that system inside of Google, and the first customer was the AdWords system, and over time, more and more internal products that we also expose externally were built on top of Spanner. So Gmail is, for instance, one of them that is also built on top of Spanner. So what is Cloud Spanner? So now you can imagine, like if you build a tool internally, you build it differently to when you actually want to make it available as one of your services in your cloud platform. So we had to add and change a couple of things. One of the very first and very important things is that we wanted to expose this as a fully managed solution. So you go, and I'm going to demonstrate that later, that you basically go there, you click how many nodes you want to have, you say okay, and you get an instance, and it's fully managed for you behind the scenes. We, of course, also wanted to expose all the things that we had internally in terms of like schema, asset transactions, things like that. Spanner has a synchronous automatic replication across all the replicas. So this can be for one zone or one regional setup. You have multiple zones where it's replicated. If you have a multi-regional setup, it will be across the globe where it's replicated. And if you bet on Spanner, if you go today to Spanner and try it out, and you want to use it in production, you can be sure that this, like the Spanner version that we expose external at Cloud Spanner, is the Spanner that we use internally as well. So it's not like a rewrite of a product; it is the actual Spanner. So the same SREs that take care of keeping that system alive for our business will take care of keeping this alive for your business. Now. With making that available for cloud, we also had to add a couple of features which are working differently inside of Google. So we wanted to integrate it, of course, with all the goodies that we have already existing in cloud platform, things like encryption by default, things like IAM, so identity and access management integration, integration with logging, having a lot of client libraries available so that you can get started. So we have right now Java, Python, Go, Node.js, and more are coming. You have a REST API that you can use, or gRPC stuff if you want to build your own. libraries. And we initially made it available, GDBC driver available, but this one is read-only currently. So how does Spanner compare to, like, on the one hand, a traditional relational database system, on the other hand, to a non-traditional database system? So now, if you look at Spanner versus a traditional RDBMS, be it your like big database vendor, be it a MySQL, or be it a Postgres, you can basically check like the schema, existing SQL consistency existing, but where it already like diverges is like availability and scalability. So if you look at, for instance, a Postgres system, if you want to scale, you can scale vertically, but at some point you run out of headroom in terms of like bigger machines. If you approach that, and you are with a cloud provider, you can just hope that that cloud provider provides you a bigger machine so that you can move over, but it's basically bounded by vertical scalability. Now, there are some tricks to get a little bit more write capacity into your master of like your Postgres or MySQL setup, and that is usually that you take away some of the read throughput from your master, and you do that by setting up a read replica, for instance. Now, another thing is like in terms of availability, what you usually do in these setups is having like a hot standby. So you have a master-slave replication where in the case of a failover, you fail over to your slave. But what that usually means is you have a little bit of downtime. Even if that is a planned maintenance, if you plan that failover to basically do security updates of your master and things like that, you accrue some downtime to fail over to your slave. Now, this gives you still like only like a certain like capacity in terms of scalability. And then like if you outrun this capacity, what you usually do is you go to like a sharded system that you have like multiple MySQL, and then you build like on top of application layer that take care of like transaction semantics and things like that. So you can't like take these, you basically lose to some extent the capabilities of the underlying database system by building like a sharded system. Now, if you compare it to a non-relational system, you basically go into the world of like not having like strong consistent schemas anymore. You're going into the world that you might not have SQL support anymore, and you go into the world that you have sometimes configurable consistency, but usually if you want to scale horizontally, this is like very restricted in the way what you can do. Otherwise, if you basically configure, for instance, with a Cassandra, strong consistency over a lot of groups, then you basically restrict the scalability that you have. Another thing is like if you compare it, for instance, with Cassandra, you basically set up your sharding, and if you need to reshard, that is like a very tedious and complicated thing to do. Now, what are like usual or like typical use cases for Spanner? And I just want to pick out a couple of them. So one of them is basically, we get asked like, okay, Spanner is for like big data. I don't have terabytes of data. Can I still use it? Does it still make sense to use it? And it definitely makes sense. So since Spanner is horizontally scalable and replicated and automatically replicated, it means you can use it for as a mission critical database. So by default, Spanner is high available. It's a high available system. Right? Now, on the other end, of course, also like since you have this horizontal scalability, if you need a system which scales for your writes and reads, then Spanner is also a typical use case where you can go. Another thing what we see is like for data consolidation. So if you have a scenario where you, for instance, you have your RDBMS that has your account data, and then you have another system where you have logs, and then like at the end of the day, you ETL data around to join your accounts with your log data to do some analysis of how your user is using your system. Now you have the possibility with Spanner to basically consolidate that all in one system and run these things in one system. What's really important here is like Spanner is strong, consistent And the strong consistency in terms of the level is serializability. So it's the strongest level of consistency that you get with Spanner by default. Now, how does Spanner work under the hood? So if you look at Spanner, it's let's assume we have a regional instance. Now, with the regional instance, basically, if you choose one node from us, if you configure your regional instance with one node, you get a node in each instance. So that is your high availability, and it's your application as well. Now we separate compute and storage. So by doing that, we enable the horizontal scalability. So basically, we have the compute nodes on the one hand, and we have the storage in all these zones as well, where we basically store the data. Now, if we want to scale, we basically can add compute nodes, and they will figure out basically what data part they are responsible of. So how does it look like? Like how does it work in terms of like the horizontal scalability, where we look at the data responsibility of a node? Now, to go into detail about this, I want to cover a couple of like concepts within Spanner. So first, we have the instance. An instance can have multiple databases, up to 100 databases, and then each database has like up to I think 1,000 tables. Can have up to 1,000 tables. So these are the concepts that are exposed to the user that you see, that you can actually deal with. Now we have also a concept behind that we deal with to enable the horizontal scalability, and that are splits and tablets. Now, what is a split? So basically what we do to be able to give the data responsibility of a table to multiple nodes, and with this scale, we split these tables up by the primary key in a lexicographic order. So we basically use ranges that we split that table into. And then we need like a construct that we use in our Paxos group, which I'm gonna go into detail in the next slide, where we basically, that Paxos group is responsible for. So that is, we call a tablet, and that tablet can have multiple splits. Now, this might be a little difficult and confusing in the beginning, but what it basically means is like it can be multiple splits from different tables that are like in one tablet, and then the Paxos groups takes care of that tablet. So how does it look in detail? So let's have the example of, we have our regional instance, we have these 3 nodes, the blue ones right now. And we do a Paxos group. So first thing that we do is we select the leader in this Paxos group. And then basically like each of these nodes is responsible for the tablet. So the tablet again can have different splits from different tables in there. But the tablet, if what you see here, is replicated in these 3 regions and these zones. So it has exactly the same splits in them. And then basically with Paxos, we select the leader, consensus, we use consensus, and then we basically have 2 followers and a leader. Now, what's really important here to be sure that we definitely are a strong, consistent system is that we have to make sure that we never have 2 leaders for the same data piece. And that was something that Google invented and is very novel in terms of like how Spanner works, is that we invented a system which quantifies uncertainty in terms of time. What does that mean? Now, if you basically sit next to your neighbor and you compare your watches and you synchronize them, and then you go off and come back, your watches will be out of sync. That is dependent on like temperature, isomorphic rays, things like that. So it's really difficult to actually synchronize data centers around the globe to be like have like the same wall clock time. So you cannot just take a timestamp and be sure that that timestamp hasn't passed on in a different data centers. So, and if you look at this, then you have the problem that you might like select a timestamp that hasn't passed in a different data center, and by that you could end up with having 2 leaders for the same data piece. So now, of course, we want to avoid that. That's really bad. And usually the way how you avoid that in distributed systems is you avoid it with communication. Now, communication is expensive if you go across the ocean and across the water. So we want to save basically these round trip times. So what we invented is called true time. And true time basically quantifies the uncertainty in terms of like what the time, if it has passed or not. So what does it really mean? So it basically says true time gives you an interval, T1 and T2, which means that T1 has definitely passed and T2 has definitely not passed anywhere of the world, right? And to synchronize and get like this epsilon, which we call like the difference between T1 and T2, 2 epsilon, to get that very low to be fast with our spanner system, we need to synchronize our data centers, and we do that through GPS. And basically we have GPS. As you can see here, we have like GPS masters, time masters in our data centers, and we have atomic clock time masters. And then if we get a true timestamp, we basically go to a subset of these time masters, which consists of a GPS and atomic clock time masters, and then we get basically the true time interval, which quantifies like how like what definitely passed and what definitely hasn't passed. Now, if you look at like what these clocks about, like what they drift about 200 microseconds a second. And usually in our system, like if everything is up and running, we have about intervals about 2 milliseconds in our data centers. Now, if time masters go down in a data center or in a zone, then the system doesn't stop. Spanner can basically go to the next data center and get the true time timestamp from another data center, but then we add basically the round trip time in terms of uncertainty. So the interval gets much bigger, which means the system slows down, but it doesn't stop. All right. So if we look at the life of a query, like how does like reads and writes work in Spanner behind the scenes? So first, what I want to look at is a consistent read. And why do I say consistent read? I want to make the distinction between a consistent and a stale or time-bounded read. So first, we look at a consistent read. So normal select star event from a name, and I could have changed here to Spring.io. So basically what we do, the client does a request, and that comes into a zone where like a slave of that data piece is in that Paxos group. Now the slave basically contacts the leader and says like, hey, am I up to date? And if the leader responds like, yeah, like your timestamp that you have is like the data that I have, then the slave basically, or the follower responds with the data. So in this case, we don't move the data from the master or anything, or from the leader to the slave. The data is already there, and we can serve it from like the nearest point. Now, if you have if the slave asks if this is okay to read, and we get like the nope, you'll have the data soon. So basically what that means in the case that like the data is not yet in the slave replicated, then the slave will wait out the time till it has the data. So the data doesn't come with the response from the leader. The leader will just say like wait out the time till you are at that timestamp, and once you're up to that timestamp, you can basically respond to your request. Now we also have something called time-bounded reads. So if you don't need to make a strong, consistent read, for instance, outside of a transaction, and where you're fine with like having an estimate but not like the most current data, we can basically serve that from a replica. So we basically go to and say a request like, please answer me that question or that query with a time bound not later, like the data shouldn't be older than 15 seconds. So if it's within 15 seconds of my current timestamp, then like please give me the data, and the slave can check if it's up to date to that point. So now you might ask like what happens if the data hasn't been written for that tablet or that split for that query. We always like have like kind of like a tick, like a health tick. So basically the slaves are synchronized like in terms of like what their current timestamp is like regularly. So we can serve the response directly from our slave, which is good because we don't like stress our leaders in the Paxos group. Now, if we come to a read-write transaction, so read-write transactions, we we basically have a construct within Spanner which we call mutations. So what you see here up there is actually Go code, where I do an insert transaction into my talks table, and I say basically what the name of the talk is and what the timestamp of this talk is. Now, if you want to basically first fetch some information, for instance, like venue information to get the venue ID to add this talk, you go directly to the leader. So once it comes into our Google front end, it basically goes directly to the leader and say like, hey, this is a read-write transaction, so I need strong consistent reads. So we don't do a hop to the slave. We directly, when we get the request, directly route it to the leader. Now the leader acquires some logs and returns the query result, and then we basically do that update, that insert into our talks table, and that again goes directly to the leader. The leader sends the writes, basically the updates to the slaves of the Paxos group. And once we have a majority of acknowledgements from the Paxos group, so it could be the leader and one slave, we basically can release the logs and return the result or the transaction result if it was successful. So as mentioned, like Spanner comes with like the familiar traditional relational model that you're used to. So you have tables with columns, with SQL types. So we are based on ANSI SQL 2011 with extensions, and I get to the extensions in a bit. But basically, you can write your singers and album themes the way that you are used to writing them in MySQL or Postgres. Now, we have one addition. So we have no foreign key constraints, as you might be used to in MySQL or Postgres. But we have like a foreign key constraint minus, which we call interleaved tables. So interleaved tables allow you to co-locate data into one split. Now, this can be powerful, but it also has to be taken carefully. Why is that? So the thing is, like, if you, for instance, have like one row, and we take here like the thinger, for instance, like let's take the Beatles, and the Beatles have millions of songs. Then you basically end up with all these million songs under that one row in one split. And you can imagine if you were in one split, as I just explained, like how splits work and how you horizontally scale, basically, that ends up at like the responsibility of one node. So you're hotspotting on one node. Now, as you basically, if you have this scenario, you would do a different schema design to avoid that hotspotting. So if you pull out, for instance, that song table with the million songs, and have a separate table, then we can split that table by the primary key, and we can distribute among multiple tablets. So, for instance, if you add a node, or if you add 10 nodes to your Spanner instance, what we do is basically we take responsibility away for certain tablets from the nodes and give that responsibility to the other nodes. So it usually takes about between 10, 30 seconds to rebalance like the workload within Spanner. So if you have like, if you see a high workload and you add nodes, you see an effect pretty fast because we basically unload tablets from the busy nodes and give them to other nodes. Now in writing, basically nothing fancy. We basically just say like interleave into singers, and that tells Spanner to co-locate that data. Now a really great feature, an amazing feature of Spanner is that we can do no downtime schema migrations. So you basically can add and alter columns while your database is running under workload. So example, for instance, like adding like a column for a table. Now, there are a couple gotchas or anti-patterns in Spanner. If you come from designing databases in MySQL or Postgres, what is like very often used is things like, for instance, auto-increment IDs, or things like timestamp as a primary key. Now that are like bad and anti-patterns in Spanner based on how Spanner works. So for instance, if you use an auto-increment ID and you insert a lot of data, all that data ends up always in the last split, basically. Same for timestamp. So I want to demonstrate that here, for instance, like we have like the timestamp, and every time, since we basically split the table based on the lexicographic order of your primary key, if you insert or update rows that you use with the current timestamp, or like update with the current timestamp for the primary key, you end up always at the same split, and you're overloading that node, so it doesn't scale. So the way that we recommend to do, for instance, for IDs, you can use UUID version 4 as primary key, which helps you, like, which has a nice distribution. And what is also important to get a good scalability with Spanner is that you design your schema and your queries, or like your schema, based on the workload. So that you really look, we have some auto optimization within Spanner, but you really have to look as like, okay, to avoid hotspotting, there might be a couple of things that you have to change within your schema. So there are some white papers that you can look at, but I also recommend we have on our webpage on cloud.google.com/spanner. On the bottom, you have like some like use cases that we've done with customers, and there's one blog post about how Quizlist did migrate from a sharded MySQL to Spanner and what their experience was, and they look at like query times and things like that. It's really interesting. So just to say a little bit about this, Spanner is will not be the fastest in terms of like getting you like super low query times. So but the thing is, like, if you get more reads and more writes, like the query times don't go up like this. Like the query times like stay like that, right? All right. So another way to avoid hotspotting is, for instance, like using shard ID. So I used it for a demo. I built a keynote demo for our big event, like Next, that we have in San Francisco, and we go around with a roadshow. And I needed a way to basically keep track of like how many things I acquired. Let's say it this way. I'm gonna go a little bit into the detail of that demo. And I wanted to keep a counter. Now, keeping a counter where I have a lot of writes on it is like really bad. It's hotspots, of course. So what I did is basically I used the shard ID to be able to horizontally scale that counter and have like multiple sub counters, so to say, that I aggregate over if I need the aggregate value. All right, so let's have a look at a demo. So before I go into the demo, and that's really bad to see. Just a couple of points. So this is the schema of the demo that I just talked about. They're like really this demo is about a ticket sales system. So in this ticket sales system, you basically have events, you have venues, and you have in these venue seating categories. So like VIP, premium, and general seating. And then based on the event that is happening in that venue, you have different prices. So we have here the event, we have the seating categories, and then basically when an event happened, I have this ticket category, which attaches me a price to that seating category. Also, to be able to do a little bit of slice and dicing in that schema, I introduced a multi-event to represent things like a concert tour, like Phil Collins goes on the concert or Coldplay goes on the concert tour. I can basically group all these events under a multi-event. And then I have a couple of counters that I use, and of course my ticket table. So why is this a good example for using Spanner? In that case, basically, if you look at events, you want to be sure that you only sell a ticket once and exactly once. You don't want to oversell for your events, and of course you don't want to undersell. Undersell would mean you lose money. Oversell, you might end up with unhappy customers. So you want to be really sure that each ticket is only sold once. All right, so have a look at that demo. So before I go into that demo, I just want to demonstrate really quick like how easy it is to get started with. So let me see if I can do this. All right, it's maybe a little bit better to see. All right, so I give it a name. it autofills the ID for you. Then you select basically a region. So currently we only have Asia, East, Europe, and US Central as single regions available, but multi-region will come later this year. So in this case, I select Europe West, give it a number of nodes. 42 is always the right answer. And I click create, and within seconds, if the Wi-Fi holds up with me, I have a cluster at my disposal. So now I can basically start and go ahead and create a database. So I create my demo database, and I add a table, for instance, talks, and I add a column, name, string, done, and basically maybe a time or title, string. All right. And then I can, of course, like define my primary keys. In this case, I just take the name of the talk, and I add my table. Now this is also. Oh, did I? Damn it! Sorry about that. Demo fail. Add table. Quick. Talk. New columns. Name. Thing done, and to spice it up a bit, time. Timestamp. All right. Primary key. In this case, we take name and an add table. All right, and say great. Good. Okay. So that's pretty quick. If you don't miss the last step and have to do it all again. So we have now a demo database and our talk. Now, while basically I can write my applications, and of course I can also create secondary indexes as you're used to in a traditional database, but I can also, while the system is running, I can add a column and say like speaker, for instance. I forgot that. And add the speaker, and they say save. And like these schema updates are also in a transactional context, so they basically become available at a certain timestamp on that in your application. All right. Now another thing is like you might run your application and you like Easter business or Christmas businesses come up and you want to like provision some more nodes for this, or you see that your application goes up in terms of utilization. So to edit basically some nodes, you can just go and do this, and in this case I scale in. You say save, and you have 20 nodes. So it's really flexible in terms of like very quickly. You pay based on the hour, so don't scale more than once within an hour. But other than that, basically, like if you scale down after that hour, you save a lot of money, or you can save a lot of money. All right. Now, my title is also a bit about live coding. So first, what I want to show is in Java, and I have also a little Spring Boot example for later. But basically, all our libraries come with the Google like integration. So one of them is to basically start with authentication, and we have a really like simple construct to basically get the authentication from your context. So if you download G-Cloud on your laptop or computer and you set up a project, you set up application default credentials, and they can basically be picked up from your application. So that's for development, makes it very easy. Now, if you run your application in other environments, then you use, for instance, a service account where you can download a key for that. The next thing is I want to have the spanner options. So there are a couple of things that I need to set. Things like the project, the instance, and the database ID. Now the project ID can be picked up from the Google Credentials context, but I have to give it like the instance ID and the database. And then I can already start and basically get my database client, and I provide the project ID, instance ID, and database ID. And of course, if anything goes wrong, I I raise up my hands and leave, and I close the connection before I do that. All right, so we went through like the different scenarios of like read-only transactions, read-write transactions, things like that. So the first thing that I want to start with is a spanner read-only transaction. So I basically get the context of read-only transaction. So this is without logs, so I don't need it to do any logs on the Paxos leader or on the data that I'm doing. I'm getting my results, so I'm executing a query. So in this case, I basically select all the events from my table, and I mentioned extensions. So we are ANSI 2011 with extensions. Now there are a couple of scenarios where the optimizer that we currently have doesn't pick up certain like indexes and stuff like that. But as you, with any other database system where you have the possibility to give like hints, optimizer hints, we have something for Spanner as well. So in this case, as you can see, we have the possibility to force an index. So you have the possibility to basically say, okay, for my event, if I want to have the events in a certain date range, please use that event by date index if it doesn't pick it up by itself. And you have the possibility, and I'm going to show that really quick, if you query your database, and I have a prepared query here. So in this query, like that is based on the schema that we saw earlier. I have to work with this resolution here. Okay, so basically what that does is it selects like the available seats for events, and in this case I look for events in Great Britain, and I look for events that are happening between the current timestamp right now and tomorrow, basically. So if I run this query, and of course, table event not found. Oh, I'm sorry. We do this again. All right. So if I run that right now, you will see that it will take a while, and that's bad for a demo. But the thing is, basically, once, come on, what's happening? Where are my demo gods? All right. So this is like really bad time. Of course, like everybody would say, like, okay, if I have to wait for a query for 18 seconds, that's really bad time. But now if we look at the query explanation, and we look into, you can do query explains directly in our console, you will see that we read a lot of, that we scan a lot of rows, and that demo is actually under load. So I'm basically running like a workload right now against this demo database. So this takes way too long for me. And I think that something is going wrong here. So as we can see, for instance, here the event table, we do a table scan on it. And I just mentioned you have like these index hint that you can do. So let's try this. And let's hope that we actually get something better. So we have a force index equals event by date. And let me check if I did that correctly. And we run that again. And let's hope it's not happy with me today. All right, so this is still slow, still very slow. So let me try something else really quick, which should be hopefully faster. So let's do this. We do 17. We have today the 19th, and we take this away. And say 2017, 05, 20. All right, let's see if that runs a bit faster here. So now we have to mention that we have like tons of events in there. So if you see like the rows scanned right now, it's 12,000. So even for one day, we have 12,000 events in here. And if I now take out the index, and like what to mention is here also we do multiple joins here to get the availability in terms of the seed availability. So this is really like quite a complicated query actually. Another thing is that this database has about 2 billion rows of tickets and is about 30 terabyte of logical data. So just to put that in perspective. Now I could go ahead and like run that query multiple times, because what Spanner does behind the scenes is also that it optimizes based on your workload. So it will look at like what are the queries that you're running very often, and then optimize for that workload. So now since I have already workload running in behind, it's optimizing basically for that workload that I'm running behind. But I could basically over time get much better query times here. All right. So we basically fetch all our events here, and then of course we want to avoid any like injection threats. So we can use bind parameters here, and basically in this case again I'm using like from today and add like a day for getting events. So this is my read-only. I'm gonna run this, and like I hope that Wi-Fi stays with me. Maybe that's the Wi-Fi actually why that's was that slow. Curse. What's happening? Oh, of course. I forgot the most important thing. I get the result set and I'm not processing it. All right, so first thing that I want to do is, of course, I want to go through my result set. And I want to print some results in this case. Result set dot. And you can basically use either column IDs or column names in this case. String. And all right. Let's run this again. And we should get hopefully our events. All right, so this works. Now I don't want to bore you too much in terms of doing slow live coding for the rest of 5 minutes. So I just want to show really quick how a write-only transaction would look like. So you basically, and then I'm gonna run this. So basically in this case, what you do is you deal with mutations. So here what we get is basically we build mutations, and we set the account ID, the name, country code, and all these things. Now, mutations is a construct in Spanner, which I want to go in a little bit of detail on. When you do transactions to Spanner, you cannot go above 20,000 mutations for your transaction. Now, what does this 20,000 mean? Every cell that is modified in a transaction is one mutation. So now, if I have this account table and I have here 5 columns and I insert one row, that translates to five mutations. If you have an index on it with, let's say, 2 columns, then it translates to 7 mutations. So you have to keep that in mind when you run and design your transactions to not go over the limit of 20,000 mutations. Another thing is the sweet spot for Spanner in terms of transaction size is about 1 megabyte. So if you can, of course, group multiple updates and inserts together, but the sweet spot is about like 1 megabyte for a transaction. So now I have basically written my account, and if we go to my demo database, we're gonna see that the account is there. So I've like preloaded, I have my demo, and I go to my account, and I have my account here. So I just created that one. Now, for read-write transaction, I basically get transaction context, and there's a specialty here about the read-write transaction. So basically, what you do is you create this this transaction callable. And the reason for that is you basically put your transaction into this transaction callable and then give it to the Spanner client. And a spanner client will take care of things like reruns and things like that, retries. So if your transaction fails, the spanner client takes care of like doing the retry for the transaction. All right. Of course. What did I just change? Sorry. All right. So now, as we can see, we basically update our table, and I just updated the name. And the last but not least, if you want to do like things like deletes, you basically have to provide a key set to do deletes. So that can be based on your primary keys, things like that. In this case, I want to delete my entire data in my account table, so I do key set all. Again, that is a mutation that I give to the client in the right transaction, and then I execute that. So let's do this really quick. And as we can see in the table, that we now have no data. So clean up. Now the problem, we have also a Spring Boot. We are working on a Spring Boot implementation. Unfortunately, I run out of time to show you that. But what I want to give you is, if you go to Saturnism, which is my colleague Ray, he built a Spring Data Spanner implementation to work with Spring Boot. So you have the Spring Data Spanner repository, and you have the Spring Data Spanner demo, which basically gives you a sample application to do the integration with Spring Data. And we are currently working at this. It's not available in Maven Central yet, but basically once we have it in a state that we can push it out there, we're gonna do that. All right, with that. Where did my... All right. Last but not least, I only want to touch really quickly on this. A lot of people ask, like, does it defeat the spanner cap theorem? And that guy, Eric Brewer, came up with that in 2012 or when it was, 2010. And it basically says, like, you have in a distributed system, you have to choose between three things in terms of consistency, partition tolerance, and availability. Now, if you go and somebody claims in a distributed system to be a CA system, then don't trust them. The only CA system that you have is a single node, because you cannot sacrifice partition tolerance. Now you have you have systems that are available in terms of the partitioning. So if they partition, they are still available, but in that case, of course, not consistent. And then you have systems that choose consistency in the case of partitioning, where when they partition, like parts or the entire system becomes unavailable. Now, Spanner is a CP system. If we have partitioning, we result to consistency. But the thing is, the case of like network failure is super unlikely. The way Spanner is set up and distributed, the case of that we have partitioning is very, very unlikely, and a partitioning that basically results to unavailability of the Spanner system. Now, if you are like, if your applications are running in one zone where that zone basically gets cut off everything else, of course, your application becomes also unavailable. All right, with this, if you want to try it, there is a Google Cloud Platform free tier. We give you $300 for 12 months. And please try it and find me at the booth if you have any questions. With that, thank you very much.